Now let us see what is the Maxwell's equations from Ampere's law. Okay, what is the Ampere's law we have studied? From Ampere's law, we know that the closed path integral of magnetic field intensity is equal to current enclosed by the same path. It was the Ampere's law we have studied. Okay, but here if you observe, how do we find the current? If you know the volume current density J bar, if you know the volume current density, the current is equal to surface integral of volume current density. Okay, so now this entire equation is called integral form of Ampere's law. This entire equation is integral form of Ampere's law. So now this is the Maxwell's equation from Ampere's law. Okay, now let us write down differential form. To write the differential form of Maxwell's equation, just observe this one. Here we have a closed path integral left side, the closed path integral of h bar. Okay, how would I convert a closed path integral to surface integral? By using which theorem I can do the conversion? Here we already studied Stokes theorem. In the Stokes theorem, the region is a surface, boundary for the surface is a closed path. Okay, so we can convert a closed path to surface and surface to closed path with the help of Stokes theorem. Okay, and by using the curl operation. Okay, so here let us apply Stokes theorem. Stokes theorem and convert a closed path to surface integral. It is a surface integral of curl of the same vector field h bar dot ds bar, which is given by the right side equation is the surface integral of volume current density j bar. Okay, now just observe this one. On both sides surface integrals are equal. When integration surface integrals are equal, then their internal parameters also equal, or just eliminate surface integration on both sides. Okay, so we get curl of h bar is equal to j bar. Okay, so this is in terms of differentiation called as curl operation. So this is called as differential form of Ampere's law. Differential form or point form of Ampere's law. Now you just observe this one. Here this integral form of Ampere's law and a differential form or point form of Ampere's law. These two equations are called as Maxwell's equation for Ampere's law. Okay, so here from this Maxwell's equation, I am going to tell you one more important point here. Just consider this equation, del cross h bar is equal to j bar. So apply divergence on both sides. Okay, just like a differentiate on both sides. So I write apply divergence on both sides. Yeah, then the equation will be the divergence of curl of h bar is equal to divergence of j bar. Okay, now if you observe the left side term, left side we have a divergence of curl of a vector h bar. You know that already we have studied about vector null identities. Among them, the one is the divergence of curl of any vector is always equal to 0, which is called as a null identity. Okay, so this entire equation is 0, which is called as a null identity. Null identity or vector null identity. Okay, so from this equation we say that del dot j bar is equal to 0. So I am going to write here del dot j bar is equal to 0. This is the equation we obtained by applying divergence on both sides. Okay, so this equation is called KCL, Kirchhoff's current law, in differential form. In differential form. Okay, so now you need to know how it is KCL actually. So we have studied KCL in circuit theory or network theory. This is the KCL in the field theory. Okay, let me explain how it is KCL. So to understand this one, let us apply volume integral on both sides. Okay, so I do apply the volume integral of divergence of J bar into dV is equal to volume integral of 0 into dV. Now we apply divergence theorem. Divergence theorem to convert this volume integral to closed surface integral. This becomes closed surface integral of J bar dot ds bar is equal to, this right side term is 0, it is not a constant. The reason is that this volume integral finds the total volume. The total volume into 0 will give you again 0. Okay. So now just see the left side equation. So here surface integral of J bar gives which parameter? The surface integral of J bar is always given by current I here. Okay. Or you can verify with the units. J bar has units of amperes per meter square, which is a volume current density. And surface element has units of meter square. Okay. Where meter square in numerator denominator gets cancelled, you'll get units of amperes. So this is nothing but current. Okay. So simply here what you can observe here is the integration represents addition or summation. Okay. So J indicates volume current density, that is current crossing unit cross sectional area. Okay. And surface element finds area. Okay. So which is 0, where area gets cancelled. The algebraic sum of currents at a node is always equal to 0. So this is the KCL in network theory or circuit theory we have studied. Okay. So this equation is extracted or approximated from this equation. Okay. So I am going to say that. So this equation is nothing but KCL in integral form. KCL in the integral form. Okay. So simply I meant to say that divergence of J bar 0 or closed surface integral of J bar 0, these two indicates KCL in differential form and also in the integral form. Okay. This is the KCL in field theory. Okay. So now here we have studied Ampere's law till now, but here there is a inconsistency in this Ampere's law. Inconsistency means there is a situations where Ampere's law is unable to explain. That is called as inconsistency in Ampere's law. First I will explain what is meant by inconsistency in Ampere's law. Then we will see how this inconsistency is eliminated by the Maxwell. That is called as a modified Ampere's law. Okay. So that we are going to see in the next lecture. Okay.